Thank you for the introduction, Maria. So I'm Kelly, for those of you who don't know me. I'm a PhD student here working with Eduardo Martinez, and today I'll be talking about a paper we published earlier this year in JHEP by myself and this lovely group of collaborators here. And this looks at the entanglement structure of quantum fields in a way motivated by detector models in RQI. So we've already seen a bit today on the fact that because the ground states of QFT are highly entangled states, local probes or detectors are capable of harvesting entanglement from the vacuum. And it's possible to use this entanglement, for example, for assisting in information processing tasks or violating energy conditions, for energy teleportation, lots of things. But another thing that we're interested in is quantifying the entanglement between subregions of a QFT. And detectors may be very good for this also. And this is a problem that we do need to solve because standard methods of quantifying entanglement of a system directly typically run into lots of issues in quantum fields. For example, we get divergences in the continuum limit when we try to calculate the entanglement entropy between a region and its complement, or we have issues when it comes to finding entanglement between disconnected regions because these are mixed states and many entanglement measures no longer apply. All in all, we don't have a general method for quantifying the entanglement between subregions of a QFT. And this could be helpful, for example, in looking at processes like black hole evaporation. Detectors, on the other hand, are inherently regular. They have a finite spatial and temporal extent and a finite energy gap, and so we will not get UV divergences. And they also easily handle arbitrarily shaped regions, even in cases with time dependence. So they seem to be a promising and operationally motivated way of studying the entanglement structure of QFTs. But your standard entanglement harvesting protocol does not give much detail on the actual structure of entanglement of a quantum field. When I say entanglement structure, I'm referring to things like the spatial distribution of the entanglement, which degrees of freedom in the field are entangled, and perhaps even the time evolution of entanglement. Now, we can't make this direct connection between the entanglement that detectors harvest and the entanglement structure of a quantum field. For one, because the efficiency of detectors is hindered by local vacuum noise. Also because detectors have a finite number of degrees of freedom, whereas the entanglement in a quantum field is distributed throughout its infinite dimensional phase space. And finally, there's a priori no way to know if the detector's entanglement is in any way capturing all of the entanglement present in a field. And so we'd like to figure out how to use detectors to faithfully capture the entanglement structure of a quantum field. And to figure out how to do this, we can be motivated by the fact that one detector is only a single mode system, or we can define it to be. And this limits the amount of entanglement that it can pick up through any interaction with the field. But through this, we can recognize that the most efficient interaction that we can do is perform a perfect swap interaction with a field mode of our choice. This will fully transfer some field mode of our choosing into the detector and the detector state into the field. Now, it will be the case that no single mode of the quantum field will be able to capture the full entanglement structure, as the entanglement is, in principle, spread throughout all the modes. But we can figure out the minimum number of detectors that we need, as well as the exact couplings that these detectors should have to fully capture the entanglement present in a subregion. And what this paper does is provide a recipe for doing exactly that. So in this process, we model a free scalar massless quantum field as a lattice of quantum harmonic oscillators with nearest neighbor coupling. Using a lattice discretization is equivalent to introducing a UV and IR cutoff in the theory, which is convenient because it allows us to use the tools of Gaussian quantum mechanics in studying this. Our paper also discusses the generalization to the continuum limit, or how our results generalize in that way, but I won't quite have time to get into that today. So this lattice has the following Hamiltonian, where omega is the free frequency of each of the oscillators. Alpha is the coupling between lattice sites. We can see we're coupling just the position degrees of freedom of, this represents summing over nearest neighbors here. And then Q and P are the position and momentum quadratures of each lattice site. And those are related to the discretized versions of your standard field operators, amplitude and momentum, in the following way, where epsilon is the UV cutoff and n is the number of spatial dimensions. Now, because this Hamiltonian is quadratic in position and momentum, which means it represents a Gaussian state, there exists a corresponding covariance matrix, which is a matrix of the covariances, or one could say correlations between all the degrees of freedom in the system. And we usually will call this sigma. Now, sigma is the covariance matrix representing our quantum field, which, remember, we've effectively put in a box by imposing a UV and IR cutoff. And we bipartition it into two subsystems that we can call A and B. Then we can find the entanglement entropy between region A and B in the following way. First, we find the reduced covariance matrix on A by tracing out the part of the covariance matrix corresponding to region B. We could also do the reverse because the entanglement entropy is symmetric in this sense. And then we find the symplectic eigenvalues of the matrix that results, and then we just effectively add them up in the way that the formula for the entanglement entropy dictates to get the full entanglement entropy between the two subregions. So that's how we find the full entanglement between complementary subregions. But let's remember our goal here. We're not just trying to determine this entanglement. We can only do that by hand in this because of the simplicity of this lattice system. But what we're trying to do is devise a method of measuring entanglement in an operationally motivated way, which will provide a framework that we can extend to systems beyond what we're actually capable of calculating from the lattice or the field directly. And we'll use that idea of the swap interaction to determine the specific modes within a subregion that are most entangled with the other region to get the maximum amount of entanglement in a single interaction. And I should specify in this paper, we'll just be considering the case of entanglement between complementary regions. So let me be precise about what I mean when I say modes. So when we obtain the reduced covariance matrix for subregion A after tracing out subregion B, we're free to express it in any basis that we want. So our modes could simply be the modes of all the local oscillators by themselves. Or we could construct modes that are linear combinations of these degrees of freedom. Or we could find the basis in which the covariance matrix is diagonal, which would be finding the normal modes of the system. We could also take linear combinations of those normal modes. So the modes which I'm talking about here are not exactly mechanical modes in any sense, but they're rather just different linear combinations of the degrees of freedom in our system. And one choice of that corresponds to the one that would contain the most entanglement. And that mode, or group of modes, is the one or group that we'd like to swap with the state of our detector, our detectors. And so the main result of our paper here, and our paper contains the proof of this, is that the most entanglement between a region B and some group of, say, n modes within subregion A, maximizing over any possible choice of modes, in fact is found by the n most mixed normal modes of the reduced covariance matrix of subregion A. And those most mixed normal modes are identified by those having the largest eigenvalues, because remember, the entanglement is calculated purely from the eigenvalues, and the largest ones will contribute the most to the entanglement. And so with that, we have a prescription for finding the set of n modes that a detector system with n degrees of freedom would couple to extract the most entanglement with the complement region. And now further, it only takes a simple rephrasing of this result to get the spatial coupling profile, or the smearing function, that a detector would need to swap with that mode. So the mode, the normal mode, can itself be expressed in terms of its own quadrature components, which we'll call capital Q and capital P. And those mode quadratures can be expressed as linear combinations of the local oscillator quadratures, little q and little p, where the coefficients f and g tell us the spatial profiles of the normal modes in position and momentum, respectively. And to relate this to the standard particle detector language, if we take the continuum limit of these functions f and g, then that tells us the smearing function that a detector should have to swap with a given mode. Now, to kind of visualize these two, the position and momentum spatial profiles as one, we can multiply them together component-wise to get the mode occupation function. And looking at this occupation function for the most mixed mode of each subregion in 1, 2, and 3 spatial dimensions, we get the following results, where these 3 plots down here are just slices in the z-axis of this 3D plot here. Kind of see what's going on as we go through that cube. And we can see that the support of these modes are strongly concentrated near the boundary. And this is what we expect because our Hamiltonian only contains nearest neighbor interactions. And so the entanglement present in the ground state between the region and its complement will largely be shared between in the short distance correlations across the boundary. So now I can give a bit more detail or just mathematically show what the swap interaction between a multi-mode detector and some set of modes would look like. The interaction Hamiltonian for the operation that would perform these mappings here is given by that Hamiltonian. And this can also be expressed as a unitary operator or the swaperator. So with this, we have a complete description of the swapping protocol that we can in principle use to transfer some given mode of the field into our detector. But the question remains of how many modes we need in order to capture the entanglement structure of our field. Now for this quantum field, the entanglement structure is that of an area law, which means that the entanglement entropy scales with the area of the subregion size. And again, this is because we only have nearest neighbor interactions, so vast majority of correlations are right on the boundary. And while the full entanglement is distributed throughout all the degrees of freedom of the system, can use the fact that it's suggestive, the fact that correlations are right on the boundary is suggestive that we might need fewer than the full number of degrees of freedom in the system to capture the full entanglement structure. And indeed, we find that we actually only need to consider as many modes as there are boundary sites for a given system to capture the full entanglement. So in one dimension, the boundary between some region and its complement in a harmonic chain will always just be 2 sites. And indeed, we find that we only need to take into account 2 modes to recover the full entanglement entropy between the 2 regions. And these percentages, which apply to both these plots here, are representing the percent of the number of boundary sites in the number of modes we're taking into account. So for example, if there's 100 sites that make up the boundary, this corresponds to taking into account 10 modes, 20 modes, 30 modes, and we find again that we only need to take into account the same number of modes as there are boundary sites to recover the area law. In 2 dimensions, we expect the area law, which is more like a perimeter law, to be linear, and in 3D, we expect this to be quadratic, which we indeed see. And so this tells us that the number of detectors we need only scales with the area of the subregion size. And All in all, this has showed us that detectors could provide a measure of the entanglement between arbitrary regions of quantum fields. We've seen that the optimal smearing function can be obtained via a normal mode analysis of the subregion. And the next steps we want to take with this work is to determine an analogous optimal protocol for non-complementary or disconnected regions. Thank you for listening.